In this session, we'll learn about how to design the length of a taxiway. I am Ashok Kumar, Assistant Professor, Department of Civil Engineering, Walchand, Institute of Technology, Solapur. In this session, we'll learn about how to design the geometric feature of a taxiway. So, in the previous session, we got to know that what is taxiway. It is the path on an airport connecting the runways with the ramps or hangars or terminals and other facilities. Mostly, this is connected with the runway to the apron area where the passengers are going to be get in and getting out. So, this is the picture of your runway, and this is your runway, and from the runway, as soon as the aircraft is landed, so it is going to search where is the exit point. So this exit point is your taxiway, and from this taxiway they will be going towards the apron area. So first we'll understand how to design the turning radius of a taxiway. So it is in the last session we understood this is given by v square by 125, or another equation using Horn's equation we are going to get what is the turning radius, where v is the speed of the aircraft and f is the coefficient of friction, and it should not be less than, the turning radius should not be less than 120 meter and 180 meter for the supersonic aircraft. That is the minimum value for the supersonic. The minimum turning radius value for supersonic jet planes are 120 meter and 180 meter. Another equation, Horn's equation, 0.388 w square by 0.5 t minus s, where w is the width of the wheelbase of the aircraft, t is the width of the taxiway, and s is the distance between the point midway of the main gear and edge of the taxiway. So now we'll move towards how to design the exit taxiway. The first one, we are going to calculate the length of L1 and L2. So here the curve which is considered, the exit taxiway curve is considered as a compound curve. Hence, when we have a compound curve, there will be two lengths and two radiuses and two deflection angles. So first one, L1 is the entrance curve and L2 is the length of central curve, and R1 is the radius of the entrance curve and R2 is the radius of the central curve. So the equation is given by VQ upon 45.5 C into R2. That is for the length of entrance curve, and L2 is 5 into R2 into D2 by 180, where R1 is the radius of the entrance curve, R2 is central curve, L1 is length of entrance and L2 is length of central curve. So here the value of C is taken as 0.39 and D2 is the deflection angle of the central curve. So this is your taxiway. So from the taxiway, the aircraft is going to be turned towards the apron area. So this portion is called as the taxi. So we are trying to design the length of a taxiway and deciding this L1, R1, L2, R2, D1, D2. Now considering the compound curve, we have the two compound, for this compound curve we have a R1 and R2, two radiuses are there, and L1 and L2 and delta 1 and delta 2, or D1 and D2. So two deflection angles, two lengths and two radiuses. So stopping side distance, to observe the vehicle on whether the vehicle is standing on the runway or on the taxiway, the both should be visible well in advance. So the length of the stopping side distance taken as v square by 25.5 d, where d is the average deacceleration rate, it is taken as 1 meter per second square. So once we calculate the length of the taxiway, try to see that the length of the taxiway should be more than stopping side distance. So this distance is visible, available for the vehicle to see another vehicle on whether on the aircraft runway or on the taxiway. The turning radius, we know that v square by 125. With this we calculate the radius. With the example, we will understand the whole design process of an exit taxiway. So here the deflection angle is given as 35 degree, and the radius of the entrance curve is given as 731 meter, runway width is 45 meter, and taxiway width is given as 22.5 meter. So try to design the length of a taxiway and calculate the overall all the parameters and draw the detailed the diagram of the taxiway. The first one, we will proceed with calculation of the center radius of the central curve. We have two curves, entrance curve and central curve. For central curve, it is taken as R2, it is given by v square by 125, v it is given as speed of the aircraft is given as 80 kmph, and f as 0.13. So with that we have got 394 meter is the radius of the central curve. Entrance curve length VQ upon 45.5 C into R2. So here the R2 value is 394 meter and C value is taken as 0.39, and with that we have got 73.23 meter is the length of the entrance curve. Now deflection angle is given by 180 into L1 by 5 into R1. So we know that the geometry of the curve, it is the length of the curve, it is given by 5 into R divided by 180. So with same equation we try to find out what is the D1 here, that is deflection angle is I, 5 into R into I divided by 180. Putting the length and R value, we can calculate what is the deflection angle here. So if I take the I value here, that is the D value here, that comes 180 into length of the curve divided by 5 into R1. So same equation I have put it here in this one to calculate the deflection angle, that is in this case it is I here, in this case it is D1 here. So now with that we have got the deflection angle D1 for the entrance curve, it is 5 degree 45 minutes. So how to calculate the D2? So we know that the total angle here from the compound curve is I equal to I1 plus I2. So in this case, in place of I am using D, and I1 is a D1, I2 is a D2. So if I put D equal to D1 plus D2, I know D1, I know I, the total deflection angle is given as 35 degree. Put the deflection angle D and D1, I can calculate what is the D2 here. So D2 equal to 35 minus 5 degree 45 minutes. So I got 29.25 degree is the deflection of the central curve. So I have got D1, D2, L1 I have got, R2 I have got, only the remaining parameter is L2, that is the length of central curve. Again use the same equation to calculate the length of the central curve, it is 5 R2 D2 divided by 180. The same equation just now we have discussed this equation to calculate the length of the central curve. With that we have got the length of the central curve as 201.14 meter. Now we have to check the stopping side distance is available, proper stopping side distance available from the runway to the taxiway. So both vehicle must be available. So side distance is given by V square by 25.5 into D, where a D acceleration is taken as 1 meter per second square. With that we have got 251 meters. So try to see that the length of the taxi which you are calculating should be more than 251 meter. So now for the separation clearance, as for the ICAO, International Civil Aviation Organization, the minimum the separation clearance is 184 meter plus the half width of the runway plus half width of taxiway. So total 45 by 2, 22.5, and 22.5 by 2, it is 11.25. So this is the distance is called as the separation clearance. So 217.75 it is required because the wings of the one vehicle on the runway, another vehicle on the taxiway, there is chances that the both wings of the aircraft may collide each other. So this separation clearance ensure that the sufficient safety is ensured between the vehicle on the taxiway and vehicle on the runway. Now you can pause over here. Now we need to calculate the length of the taxiway. So this parameter I need to calculate here. So you can take a pause. I need to calculate the hypotenuse component from here to here. So you can think which function you use to calculate this length of a taxiway, because I know the opposite component, hypotenuse component I required, and I know the deflection angle. So you can think over here and how to calculate the hypotenuse component. I hope you are able to do that. So use a sine function here. Use a sine function to calculate this hypotenuse component. The first one, I have taken this triangle. So from this triangle I have taken the entire triangle I have taken here. So from here to here, this entire triangle is taken for calculation. So now opposite component is 217.75 and the angle is 35. Use a sine 35, that is sine 35 equal to opposite upon x. So x is nothing but hypotenuse. So x equal to 217.75 divided by sine 35. Now, but the length of the taxiway is from here to here. It means we need to deduct these two opposite the hypotenuse the parameters here. One over here and another over here. So how to deduct these two triangles, that is two hypotenuse triangles we have to deduct from this to get the length of exit taxiway. So now again the two triangles are going to come here. One triangle is here, another triangle from here. So these two triangles you can get, then again use the sine function here to calculate here. So I will take out this small triangle here. This is the one triangle. This is the first triangle here which I am going to take it. This is the first triangle. The hypotenuse component I will take it as x, and the angle is 35 degree, and the sine function I will use it here. So this opposite component, how much it is opposite component? Half of this 45 meter, that is 22.5 meter. So 22.5, so sine 35 equal to 22.5 divided by x, or x equal to 22.5 by sine 35. So same thing I have put it here, 22.5 sine 35. That is 45, for half of the 45 is 22.5. This is 45 by 2 is 22.5. This triangle is over. Now coming to this location here, another triangle is over here. Another one, again the hypotenuse component, and this the opposite component. Here this the opposite component here, it is the half of this 22.5, that is 11.25. That is 11.25 is the opposite component, and x is the hypotenuse component here. Again use this the sine 35, that is 11.25 by x, or x equal to 11.25 divided by sine 35. So same thing here, that is 22.5 by 2 is 11.25 and sine 35. So with this we get the net length of this exit taxiway. So we can calculate by this the equation, and finally we have got 320.79 meter is the length of the taxiway. Try to ensure this length should be more than the stopping side distance here. So 251 meter is less than 320, hence the whatever the calculated of length of taxiway is exactly correct. Now we have to calculate this the fillets. So fillets also we require to calculate. What are those? Yes, these are the fillets. The turning radius of the fillets also we have to discuss based on the deflection angle. So there is a table is available to calculate this fillet radius, one over here, another fillet over here. So for this we need to know what is the deflection angle here. Though the first deflection angle is 35 degree, for 35 degree what is the fillet radius, and what is this deflection angle? So this is the deflection angle is required. Here this is 35 degree. So 35 degree minus 180, 145 degree is the fillet, the deflection angle to calculate the fillet here. Now using this table, for 0 to 45 degree of deflection angle, you can, for large airport we can use 22.5 meter. In this case, our case is the large airport and deflection angle 35 degree. So with this we have got 22.5 meter is the fillet radius for this runway, and for the taxiway, as I told you, the total angle is 180 minus 35, 145 degree. So 145 degree falls in this more than 135 degree. The turning radius at the fillet radius is 60 meter for this. So we have to decide all these parameters: stopping side distance, these are all parameters, and length of taxiway. So these are the diagrams telling you, depending upon the radius, what are the fillet radiuses. These are the references I have used for preparing this presentation. I hope you enjoyed this presentation and got the idea about how to design the length of taxiway. Thank you so much.